What, you're not in the mood to laugh today? Okay, so question about the homework. So the homework, the homework is, as always, you might have noticed my homeworks are tougher than the quiz. So if you don't get too worried about the homework, if you have a lot of trouble doing it. The idea is to understand what the procedure is, really not necessarily completely doing everything in the homework. So the homework had 2 reactors. So the important thing about 2 reactors is you need to know, I already told you, you need to know design equation for a CSTR. So you also need to know design equations for CSTRs and series. Okay, so here you have to know that. Nothing you know really. If you know 1, you know 2, you know 3, but nonetheless. The concentration here is CA0. Right? You can write the design equation for reactor 1. The design equation is QCA0 is coming in. This should be equal to QCA, which is leaving, plus the reaction, which is KCAV, V1. So from this equation, you can solve for CA0 divided by 1 plus K V1 over Q. Right? So you all know how to do that. Then, of course, you can go to the second reactor, and you can write the same equation. You can write Q, in this case, instead of CA0, you'll have CA1 as coming in, right? Is that clear to everybody? And of course, then you will still have QCA2 as going out, right? Let's call it to be QCA1 here, 1 and 1. So CA1 is the concentration here, CA2 is the concentration here, okay? So QCA1 is QCA2 plus K CA2 times V2. And so from this equation, you can figure out CA2 is CA1, 1 plus K V2 over Q. And so this simply becomes CA0, 1 plus K1 K V1 over Q times 1 plus K. Right? So far so good? Okay. Then I think what I had was, so this is the concentration of A. Of course, from there you can also figure out concentration of B, because concentration of B plus concentration of A is constant, right? Because it's 1-to-1 stoichiometry. So CV2 is going to be CA0 minus CA2, right? And so you can sort of figure it out what the CV2 is. Okay, so it should be CA0 or minus that whole mass, right? And then from there you can figure, so you already know the FE is QCV2, and that's fixed. So that's basically your constraint, right? So you have fixed production, so that's your equation for G. So the unknowns in this equation, of course, are V1 and V2, and the constraint is the FB is fixed, and the minimization, of course, is the cross minimization. Right? So right now you have 2 unknowns, of course. So then, of course, what you can do is you can create a third unknown by saying, so F is the cost, and there will be, I think there will be 2 costs for that. One is the fixed cost, one is the operating cost. The operating cost is basically just the cost of FP or FA. I think I called rho A, FA naught, or something like that. Right? Plus there were some costs associated with the volume.
Yeah, what is that?
Huh?
You did, that's where I get lost.
Why do you get lost there? Well, that's the easiest part.
It's like the first line. I don't know where you get that from.
Yeah, it's just CR. I just don't know the notation. That's what I said. So the CR, I said CR times V1 plus V2. Are you confused by this constant or what?
Oh, I thought it was a pi. What's a pi?
There's no pi.
Oh.
Might be R, I guess.
Oh, that's an R? Oh.
No pi. I love putting pies everywhere, but especially on Thanksgiving time, it seems very appropriate.
That was a good joke.
It's a good joke?
Yeah,
Seriously?
They're getting better. Yeah.
Are you serious? Oh my God. Thank you. me that.
So
What?
would your Laplace function basically be
Lagrange.
Lagrange function? Would it be
Yeah.
f minus lambda
Exactly.
fb
Minus lambda times g.
times fb, right?
Huh?
Minus lambda times fb, right?
No, because remember, constraint is something equals to 0. Fp is not equal to 0. So it'll be Fp minus this expression, the q times Cv, which has to be, everything has to be times of V1 and V2, right? So basically you plug this in there. Plug everything. So basically the idea is that you had two unknowns, V1 and V2. Now you have three unknowns, the third one being lambda. You differentiate this. So now the first thing is now, actually even before starting the whole problem, you could have actually argued that V1 must be equal to V2, right? And you could have solved the problem that way. But in this problem, I wanted to show you how it is easy to prove that. So I didn't actually make that assumption. What I did was at this stage, so this is G now. So now the G is a function, of course, is V1, V2, and lambda. And then, of course, you have to take derivative with respect to V1 with respect to V2. And then when you do that, you use those two equations to right away see that V1 has to be equal to V2. Okay? And then you can call V1 equals to V2 equals to V. Write lambda in terms of that V. Plug it back into G, and you can solve for everything. Okay? Now the final equation may turn out to be an implicit equation, but if you get to the point you say this equation has to be solved to find V, that's fine. Okay? Which is what I think this is. I don't remember, but I don't think there's a final analytical solution to that. Yeah.
Can you explain what those first two terms are? G equals.
No, this is not G. I was writing for G, but then I finally went to F bar. This is F bar. Okay. This is the cost of the reactant. This rho A is the, I don't know if it's rho A or whatever the notation is, but this is represents the cost of the reactant, Fa naught, right? And which is basically Q times C naught. And then of course, yeah, this represents the cost of the reactors, and this last one represents the constraints. Yeah.
So we're assuming the volumetric flow rate doesn't change from inlet to outlet. Is that how you write that constant?
Yeah, the volumetric flow rate, you almost always make that assumption unless there are molar changes. Now if it's a liquid reaction, there's never a huge change in volume. If it's a gas phase reaction, in that case if your molar ratios are 1 to 1, then you still don't have volume change. Yeah? No, there's no gamma. Where is gamma? Lambda. Lagrange multiplier. Okay. So anyway, but what's the take-home message for this? The take-home message is you need to know design equations for reactors in series. Okay. As I told you, your problem is not going to be so complex with multiple terms and complications, but nonetheless, you need to know design equations for CSTRs in series. You need to know design equation for Poisson flow in a tube.
Why do you take the derivative in respect to lambda and Fa naught? That's what I didn't understand.
F naught doesn't depend on lambda, derivative will be 0.
That's what I thought too, but you took the derivative in respect to Fa naught.
Well, F naught is also unknown, right? Because Fb is constant. So F naught is not fixed. Fp is fixed.
But
Right? Yeah, so the flow rate is, I mean, the production of B is fixed, but Fa naught will depend upon the conversion. Right?
okay.
So Fa naught is unknown. Fa naught and volumes are unknown. Okay.
What
Yeah.
about-
Any question?
Why just take the derivative in respect to lambda?
You do take derivative with respect to lambda and you get back the constraint.
Okay.
So you take derivative with respect to every unknown, and then you also take derivative with respect to lambda. All right, so yeah, but let me remind you what you do need to know, at least for this quiz. You need to know the design equations for CSTRs in series. You need to know flow, Poisson flow through a tube, or laminar flow. The problem 2 here was turbulent flow, but don't worry, I'm not going to give turbulent flow. So laminar flow, and then heat transfer across a pipe, where the pipe is treated as a thin shell. So you can still use rectangular coordinates. Okay, those are the 3 things you must know. Okay? And I've already made the quiz. It's actually, there's only one problem. It's actually not a difficult problem. So you all probably will be out of here in like 10 minutes. Okay? So feel free to make plans starting 3:15. Yeah. What? Heat transfer through a pipe where you treat it as a thin shell. So you don't have to take the log terms. Now, you're talking about the LMTD?
Well, that's what I was going to ask.
The heat, there's no problem here on heat exchanger design. So, but in the final, they might very well be.
So that was the reason why sometimes we wound up with the denominator has the LN term. It's like the H times LN ratio of the area versus 1/H.
Yeah, so we will not use that equation.
That was rectangular, or that was
cylindrical taking into account curvature.
Right, okay.
So we're not going to do that.
So the worst we would have is like 1/H plus T/K kind of thing.
Exactly.
Okay.
All right, any questions? Okay, let's see. We don't have much time left. 42, yeah, only a few minutes. Yeah. I haven't entirely decided. It is cumulative in the sense that you do have to understand the concepts, but it's not cumulative in the sense I'm likely not going to give you numbers for every and then ask you to calculate, the payback period and all that kind of stuff. So yeah, it is sort of cumulative in the sense you need to know how to move money, but more or less it is not cumulative. Does that answer your question? Does that cryptic answer your question?
Yeah.
I like being unpredictable. All right, any other questions? No? Then I guess there's not much time left, so yeah, we'll just